Okay, so, sorry, is there a question? I hear some voice in the background. Maybe it's better. So we have a vector space, and we have the idea of dimension, and we're going to be looking at finite dimensional vector spaces. So if the dimension of the vector space V is n, you have various bases for the vector space. So a basis is a set of vectors, E1 up to En. Call this one E. And every vector in the vector space is a unique linear combination, x1 E1 plus x2 E2 and so forth up to xn En. And the x sub i's are the coordinates. So if I want to write the coordinates of the vector V with respect to this basis E, I like to write these as column vectors, x1, x2 up to xn. So these are the coordinates of the vector with respect to the basis, but there are a lot of different bases. Suppose we have another basis. I'll call it F. It also has n vectors because the dimension of a vector space is well defined. Every basis has the same number of vectors. And if we write V as a unique linear combination of the vectors in the basis F, that's y1 F1 plus y2 F2 up to y sub n F sub n. And the coordinates of V with respect to the basis F, y1 up to yn. So these two vectors look different because they have different numbers in them, but they refer to exactly the same vector V. These are the coordinates with respect to different bases. So let's look at an example of this. Suppose I take the vector space to be the ordinary three-dimensional space R3, and E1 will have these basis vectors. This is what is called the standard basis, 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. And let me take another basis. I'll call it F. This basis will have as its basis vectors, well, F1, F2, F3. So F1 is the vector 1, 1, 0. F2 is the vector 1, 0, 1. And F3 is the vector 0, 0, 1. Sorry. I want to make this vector F3 0, 1, 0. So again, you have to prove that this is a basis for the vector space and this is the basis of a vector space, right? But it can be done and it's not hard. So let's suppose it's done. So what does it mean to write a vector with respect to a basis? So let's just choose a random vector. I don't know. Suppose I let V be the vector 2, 3, 4 in R3. Now, the standard basis is very simple because when we write the vector 2, 3, 4, this is 2, 0, 0 plus 0, 3, 0 plus 0, 0, 4. That's 2 times the vector 1, 0, 0, 3 times the vector 0, 1, 0, 4 times the vector 0, 0, 1. So with respect to the standard basis, this is 2e1 plus 3e2 plus 4e3. So for this vector v, the matrix for v, the coordinate vector for v with respect to the standard basis is in fact exactly the same thing. That's why the standard basis is called the standard basis. But what I want to calculate is the coordinates of v with respect to the basis v, f, basis f. What is that? So I want to write 2, 3, 4 as some linear combination of f1, f2, and f3, right? What are these coordinates? This is y1 times the vector f1, which is 1, 1, 0, y2 times the vector 1, 0, 1, y3 times the vector 0, 1, 1. If I add these vectors up, what I get is y1 plus y2, y1 plus y3, y2 plus y3. So this is a system of linear equations I have to solve for y1, y2, and y3. This is equal to the vector 2, 3, 4, right? So that means we have to solve the equations y1 plus y2 equals 2, y1 plus y3 equals 3, y2 plus y3 equals 4. If I take these two equations and I subtract the second from the first, I get y2 minus y3 is minus 1. This says y2 plus y3 equals 4. If I add, I get 2y2 equals 3. So y2 is 3 halves. If y2 is 3 halves, y1 is 1 half, because y1 plus y2 equals 2. If y2 plus y3 is 4, y3 is 5 halves. So we get that the vector 2, 3, 4 is a half vector f1, 3 halves vector f2, 5 halves vector f3. So the matrix, the coordinate vector for v with respect to f is a half, 3 halves, 5 halves. Right? But again, you have to understand exactly what this means. This is not the vector in 3 space with coordinates a half, 3 halves, 5 halves. This is the vector in 3 space, which is the linear combination a half f1 plus 3 halves f2 plus 5 halves f3, where f1, f2, f3 are these 3 vectors in our basis. So when you have a basis, you can represent every vector as a linear combination of the vectors in the basis uniquely. And the coordinates are the coordinates of that vector with respect to the given basis. Here I had the standard basis. The coordinates are 2, 3, 4. Here I have a different basis. These are the coordinates. This set of coordinates is different from this set of coordinates, but they represent exactly the same vector. Okay. And it's easy to compute what is called a change of basis matrix, which converts the vectors with respect to one basis, the coordinates of the vector, to the coordinates of the vector with respect to a different basis. Okay. Any questions about this? This is all right. So I'll come back if I have time and compute a change of basis matrix, but I want to go on to linear transformations. So we have the idea of a linear map or linear transformation from one vector space to another. And let's suppose these are finite dimensional vector spaces. And let's see. Suppose I let E1 up to En. So these are different vector spaces. So they don't have the same dimensions. Let's say the dimension of V is N and the dimension of W is M. So E vectors E1 up to En, this is going to be a basis for V, and let F1 up to Fn be a basis for W. So T is completely determined by what it does to the vectors E1, E2, and so forth up to T of E sub n, because given a vector V in V with the coordinate vector of V with respect to E being this n-dimensional column vector, which means V is equal to x1 E1 plus x2 E2 up to xn En, then T of the vector V is T of x1 E1 plus x2 E2 up to xn En. And because T is linear, this is x1 T of E1 plus x2 T of E2 up to xn T of En. It's this linear combination of the vectors T of E1 up to T of En, which are sitting in W. But T is completely determined by how it operates on these n basis vectors. And T of EI, or let's say T of EJ, is in W. So T of EJ is some linear combination of the M basis vectors in W. T of EJ is some Aij F sub I for J going from 1 up to N. So let me rewrite this again, just write it down again. So I have the vector V in V. V is summation xj ej. J goes from 1 up to N. Okay. And T of V is summation J goes from 1 up to N, x of J, T of EJ, because T is linear. And T of EJ is in W, so it's summation Aij F sub I in W. I goes from 1 up to M. So if I take this and I plug it in there, what do I get? I get T of V is summation J goes from 1 up to N, x sub J, T of EJ, which is summation I goes from 1 up to M, Aij F sub I. I can interchange finite summations. This is a sum. I goes from 1 up to N, J goes from 1 up to M, aij xj times f sub I. So the basis, the coordinate vector for v with respect to E was x1 up to xn. The coordinate vector for T of V with respect to the basis F in W, let me call this is summation I goes from 1 up to n, y sub I, f sub I. I'm just calling this y sub I, where yi is summation aij xj, j goes from 1 up to m. Sorry. I goes from 1 up to m, j goes from 1 up to n. So this is y1 to y sub m. Right? What are these numbers? So this should look familiar. This is like you get this number if you had the row vector AI1, AI2 up to AI n multiplied into the column vector x1, x2 up to x of n. That gives you this ith coordinate. And in fact, if you take the matrix A11, you just use these as the coordinates of their matrix, A11 up to A1n, AM1 up to AMN. Here I have AI, A1, J down to AMJ. For each J, Aij, I going from 1 to M, it's this column vector. It's the jth column of this matrix. And this matrix represents the linear transformation. If you take this matrix A times the vector x1 up to xn, you get the vector y1 up to y sub m, that is the coefficients of T of V with respect to the basis F. So this is the central fact about linear transformations and matrices. If you have a linear transformation from a finite dimensional vector space to another finite dimensional vector space, for every choice of basis for V and W, you get a matrix that allows you to compute the linear transformation on any vector in the vector space. So there were a couple of examples of this in the homework, and I want to go over them. So let's take a look. This was, I think, on page 53. So I'm going to spend the rest of the period, I think, doing problems 1 and 2. And again, as I do them, if you have any questions, you need to interrupt me and ask me to explain.
Yeah, Professor.
Yes, sir.
I think last week you did page 53, problem 1.
Well, I understand that, but there are still some questions.
Oh, okay. Oh, okay.
To go over it again.
Okay, thank you.
So this is page 53, exercise 1. So there's a linear operator from R2 to R2 defined by T of xy is 5x minus y, 3x plus 2y. And in part A, we use the standard basis, E, which consists of the vectors. I wrote it this way, for example, what's on E2? E1 is 1, 0, and E2 is 0, 1. So T of E1, that's T of 1, 0. When X is 1 and Y is 0, this is 5, 3. And T of E2, which is T of 0, 1, is 0, 1 is minus 1, 2. I should say this is minus 1, 2. So this means minus 1 E1 plus 2 E2. This means 5 E1 plus 3 E3. And the matrix for T with respect to this basis, 5, 3, right? This is the column vector for T of E1. This is the column vector for T of E2, minus 1, 2. So I really should write this like this. If I take T of E1, the column vector for that with respect to this basis is 5, 3. If I take T of E2, the column vector for that with respect to this basis is minus 1, 2. And these give me the two columns of my matrix. Okay. Okay. In the second part of the problem, we take a slightly different basis. It's only slightly different, so it's not going to be much harder, but we have the same linear map, and we're looking at the basis, which I called B1, which consists of two vectors. I'll call this, say, F1 is the vector 11, 0, and F2 is the vector 0, 7. So what is T of F1? That's T of the vector 11, 0. If I plug in X equal 11 and Y equals 0, I get 55, 33. But I need to write that as a linear combination of these two vectors. This is, I'll make it easy, sort of somewhat easy. This is 55, 0 plus 0, 33. This is 5 times 11, 0. And this is 33 over 7 times the vector 0, 7.
Professor.
Yeah.
So when you talk about the linear combination, there's no that you're not referring to like a specific combination, like as long as it equals 55, 33, it's okay.
There's only one way to do it. It is specific.
Oh, okay, okay.
There's no other way you can do it because this is a basis. Right? This is 5 times F1 plus 33 over 7 F2. There's no other linear combination of F1 and F2 that would give this vector. Right? There's no other way to do it. Right? These two vectors form a basis, so every vector has a unique linear combination as the sum of a unique linear combination of these two basis vectors. What is T of F2? That's T of 0, 7. When I plug in X equal 0 and Y equals 7, I get minus 7, 14. That's minus 7, 0 plus 0, 14. Let's see, this is minus 7 over 11 times the vector 11, 0 plus 2 times the vector 0, 7. That's minus 7 over 11 F1 plus 2 F2. So let me try and keep this on the same page. So this says that if I take T of F1 and I write it as with respect to the basis F, the coordinate vector is 5 33 over 7. If I take t of f2, the coordinate vector with respect to f is minus 7 over 11, 2. So my matrix for t with respect to f, this is the first column, 5, 33 over 7, and this is the second column. So this is the matrix for this linear transformation with respect to f, and this is the matrix with respect to the basis E. Okay. It's the same linear transformation. It's the same linear transformation. It's just with respect to a different basis, so I get different matrices. All right. Any questions about that?
Oh, Professor,
Yeah.
which one is the matrix for with respect to the basis B1?
I'm sorry, there's no V1. There are two bases. One is E and one is F. Right? I had E. This is E. This is the standard basis. This is B1. Sorry, B1 is the second basis. So sorry, I called it F here. I should have called it B1. Thank you. So the matrix for T with respect to B1 is this matrix.
Okay, so that one is 5. Could you tell me that matrix?
Exactly these coordinates, 5 and 33 over 7. And the second column is minus 7 over 11, 2. Right?
Okay,
First
thank you.
column, second column. All right, let's do part C. So here we have another basis, which I called B2, which consists of the vectors 11, 0. Sorry, 1, 1, and minus 1, 1. So let me just give this a name so I have a letter for it. This is G1 and this is G2. So I have a new basis, 1, 1 and minus 1, 1. And again, T of the vector xy is 5x minus y, 3x plus 2y. And I want to find the matrix of this linear transformation with respect to this new basis. So I have to know what is T of G1. It's T of the vector 1, 1. When x and y are 1, I get 4, 5. But I have to write this as some linear combination of my two basis vectors, A11 G1 plus A21 G2. Right? I have to find these coordinates. This is A11 times 1, 1 plus A21 times G2, which is minus 1, 1. If I add these vectors, I get A11 minus A21, A11 plus A21. So I have to solve the system of two equations and two unknowns, just a standard high school problem. A11 minus A21 is 4. A11 plus A21 is 5. If I add these equations, I get 2A11 equals 9. So A11 is 9 halves, which means A21 has to be 1 half, because 9 halves minus a half is 4. 9 halves plus a half is 5. So T of G1 is 9 halves G1 plus a half G2, or the coordinate vector for T of G1 with respect to this basis B2. The coordinates are 9 halves and 1 half. So this is going to give me the first column of the matrix for the linear transformation. Right? Any questions about that? Right? I mean, this is a slightly complicated calculation, but this is what you have to learn how to do. What about T of the second basis vector? T of G2, which is T of the vector minus 1, 1. So when X is minus 1 and Y is 1, this is minus 6. When this is minus 1 and 1, this is minus 1. So minus 1, 1 is minus 6. Minus 1, 1 is minus 1. Minus 6 minus 1. And I have to write that again as a linear combination of G1 and G2, which means A12 times the vector 1, 1 plus A22 times the vector minus 1, 1. That's equal to A12 minus A22, A12 plus A22. This equals minus 6 minus 1. So I'm solving again 2 equations and 2 unknowns. The equations are A12 minus A22 equals minus 6. A12 plus A22 equals minus 1. If I add, I get 2A12 equals minus 7. So A12 is minus 7 halves. Minus 7 halves minus 5 halves would give you minus 6. So A22 has to be equal to 5 halves. And if you add, you get minus 1, and subtract, you get minus 6. So T of G2, the coordinate vector for this with respect to this basis B2 is minus 7 halves, 5 halves. So the matrix for T with respect to this basis, this is the first column, 9 halves, 1 half. This is the second column, minus 7 halves, 5 halves. So this is the answer to this problem. So again, you want to, oops. Yeah, I'm recording. So again, you want to make sure that you understand these calculations. They're very important. Any questions about this? All right. Then I will go to problem 2. So problem 2 is more complicated because here we have a linear map from R3 to a different vector space, R2. And this is defined by T of the vector X, Y, Z. It has to be a 2-dimensional vector. It's going to be 5x minus y plus z, 3x plus 2y minus z. So in part A, we use the standard bases. So E3 is the standard basis for R3, namely 1, 0, 0, 0, 1, 0, and 0, 0, 1. And E2 is the standard basis for R2, which is 1, 0, and 0, 1. So let me call these vectors E1, E2, and E3. And just to have different letters, I'll call these F1 and F2. Okay. So how do we find the matrix for this linear transformation? So for the standard basis, it's very easy. So what is T of E1? That's T of 1, 0, 0. That's 1, 0, 0. You get 5, 3. Which is simply 5 times 1, 0 plus 3 times 0, 1. So that's 5F1 plus 3F2. So T of E1, that vector with respect to the basis E2, the coordinates are 5, 3. T of E2 is T of the vector 0, 1, 0. When x and z are 0 and y is 1, you get minus 1, 2, which is exactly minus 1 times F1 plus 2 F2. So T of E2 with respect to the standard basis is minus 1, 2. And T of E3, T of the vector 0, 0, 1, when x and y are 0 and z is 1, you just get 1 minus 1, which is F1 minus F2. So T of E3 with respect to this basis E2 is 1 minus 1. So the matrix for T is going to be equal to first column, second column, third column, 5, 3, minus 1, 2, 1 minus 1. Exactly what you would expect. And you can see that if you do your matrix multiplication, T times X, Y, Z is 5 minus 1, 1, 3, 2, minus 1 times X, Y, Z. You get 5x minus Y plus Z, 3x plus 2y minus Z, and that's it. Yeah, exactly what you should get. So that's pretty straightforward, I think. Any questions about this part of the problem?
Oh, Professor,
Yes, sir.
could you explain what's going on T of E1?
Right over here.
Yes.
Okay. So E1 is the vector 1, 0, 0. So I'm taking T, the linear map T, and applying it to the vector 1, 0, 0. When X is 1 and Y and Z are 0, I get 5, 3. So the coordinates are 5, 3. But I want to express this in terms of my basis, 1, 0, and 0, 1. But 5, 3 is 5, 0 plus 0, 3, which is 5 times 1, 0 plus 3 times 0, 1. So, I mean, this is a correct calculation. And 1, 0 is the basis vector F1, and 0, 1 is the basis vector F2. So if I write T of E1, the coordinates with respect to the basis E2 are 5 and 3. So that's the coordinate vector. T of E1 is 5 F1 plus 3 F2 in this notation. All right. Does that make sense?
Yes. Thank you.
Okay. So let's look at part B, which is much more complicated. So this is 2B. Again, T of X, Y, Z is the vector 5X minus Y plus Z and 3X plus 2Y minus Z. So T is a linear map from R3 to R2. And in R3, now I'm choosing the basis, which I called B3, which consists of the vectors 1, 1, 0, 1, 0, 1, and 0, 1, 1. And in R2, I choose the basis B2, which consists of the vectors 1, 1, and 1 minus 1. Right? So this is a basis for R3. This is a basis for R2. Let me give these vectors names. Maybe I'll call this A1. Well, maybe not A1. I'll call this F1, F2, and F3. And I'll call this G1 and this G2. So just so I have names for these vectors. So what I need to do is I need to compute T of F1, that's applied T to the vector F1, and find its coordinates in R2 with respect to this basis B2. And I need to compute T of F2 and find its coordinate vector with respect to the basis B2. So what does that mean? T of F1, that's T applied to the vector 1, 1, 0. Right? 1, 1, 0, when X is 1, Y is 1, and Z is 0, this is 5 minus 1, this is 4. When X and Y are 1 and this is 0, 3 plus 2 is 5. So T of 1, 1, 0 is the vector 4, 5. But I have to write this as a linear combination of the vectors G1 and G2. I have to write this as some A11 G1 plus A21 G2. Or that means A11 times the vector 1, 1 plus A21 times the vector 1 minus 1, which is, if I had put this just do my arithmetic, this is A11 plus A21, A11 minus A21. So I have to solve my high school algebra problem, 2 equations and 2 unknowns. A11 plus A21 equals 4. A11 minus A21 equals 5. If I add, I get 2A1 equals 9. So A11 is 9 halves. A11 is 9 halves. A21 is going to be minus a half, because A11 plus A21 is 4. 9 halves minus a half is 8 halves is 4. 9 halves plus a half is 10 halves is 5. So the coordinate vector for T of V1 with respect to this basis is 9 halves minus a half. So I'm half done the problem, right? I found that. What is T of F2? T of F2 is T applied to the vector. Oops, sorry. I also need T of F3. Need all 3 of them. T of F2 is T applied to the vector 1, 0, 1. When X and Z are 1 and Y is 0, this is 6, 2. And we have to write 6, 2 as a linear combination of G1 and G2. This is some A12 G1 plus A22 G2. Which is what? A1, 2 plus A22, and the second coordinate is A12 minus A22. And that has to equal 6, 2. So we're solving the linear equations. A12 plus A22 equals 6. A12 minus A22 equals 2. If I add, I get 2. A12 equals 8. So A12 equals 4. 4 plus 2 is 6. So A22 is 2. Right? That's solving these equations. So the coordinate vector for F2 with respect to B2 is 4, 2. Okay. Any questions about these? All right, so let's do an experiment. This is the experiment. What is T of F3? So F3 is the vector 0, 1, 1. This is my linear map. When X is 0 and Y and Z are 1, I get 0, 1. And I have to write 0, 1 as a linear combination of G1 and G2. So some A1, 3, G1, 1, and A2, 3, G1. That's A1, 3 times the vector 1, 1, plus A2, 3 times the vector 1 minus 1. So I have 0, 1. Excuse me 1 second. Yeah, sorry. So, so 0, 1 is A1, 3 plus A2, 3 and A1, 3 minus A2, 3. So again, I'm solving two equations and two unknowns. A1, 3 plus A2, 3 equals 0. A1, 3 minus A2, 3 equals 1. If I add, I get 2A1, 3 equals 1. So A1, 3 is a half, and A2, 3 has to be minus a half. So the vector of coordinates of T of F3 with respect to B2 is 1/2 minus a half. So if my calculations are correct, I hope they are, then the matrix for T with respect to these bases is 9/2 minus a half for 2, 1/2 minus a half. And that would be the answer to the problem. So what this means is, if you let V be a vector in the vector space R3, and V, its coordinates with respect to the basis B3 is x1, y1, z1, then T, this matrix, applied to this vector, gives you the vector, the coordinates of the vector with respect to B2. So let's do an experiment and see whether this makes sense. So let's check. Suppose I take a vector V, and with respect to the basis B3, its coordinates are, let's say, -2, 0, 3. So what is T applied to this vector? That's equal to my matrix, 9/2 minus a half, 4, 2, a half minus a half, applied to -2, 0, 3. Let's see if I can calculate this. I get -9 plus 3/2. That's -9 is -18/2 plus 3/2 is -15/2. This times this is 1 minus 3/2 is -1/2. So this should be, if I take T of V and I write it with respect to B2, that's what this should be. Huh. Now, let's try to disentangle this. To say that if I take the vector V in R3, and V written with respect to B3 has coordinates -2, 0, 3, this means V is equal to -2 F1 plus 0 F2 plus 3 F3. What was F1? F1 was 110. What is F2? 101. What is F3? 011. So this is -2 -2 plus 3, 3. So if this calculation is correct, let's see, -2, 110, 0 times this, 3 times this. So this is -2, 1, 3. That's what my vector v is. So T of v, just going back to the original definition of my linear transformation, this is my linear transformation. This is T of -2, 0, 3. When x is -2 and z is 3, this is -10 plus 3, this is 7. When x is -2 and z is 3, this is -6, this is -9. So T of v is 7 minus 9 in R2. And I want to write this as a linear combination of my new basis in R2. I want to write this as, I don't know, let's just say Z1 G1 plus Z2 G2. So Z1, that's my unknown. What is G1? G1 is 1, 1. And Z2 and G2 is 1 minus 1. So that's Z1 plus Z2, Z1 minus Z2. And we want that to be 7 minus 9. So I want to solve the equation Z1 plus Z2 equals 7, Z1 minus Z2 equals -9. If I add, I get 2Z1 is -2. So Z1 is -1, which means Z2 has to be equal to 8. So I get that T of V with respect to the basis B2 has coordinates -1, 8. And that would be great if that's what I got, but not what I got, I think. Let's just see. So excellent. So that's really good. I like that because somewhere in this process, I made some arithmetical mistakes. And now I'm just going to go back and check, which means I'm going to go through the problem again and try to be more careful with my arithmetic. Right. So secret of mathematics is to do things over and over again until you get it right. So the method is right, but the arithmetic had to have been wrong somewhere. So let's start again. I have T is the linear transformation 5x minus y plus z, 3x plus 2y minus z. Five x minus y plus z, 3x plus 2y minus z. And so T is a map from R3 to R2. And in R3, I choose the basis, which I called B3. And the vectors, I'll label them F1, F2, and F3. F1 is going to be 1, 1, 0. F2 is going to be 1, 0, 1. And F3 is going to be 0, 1, 1. And in R2, I'm going to choose the basis B2. So it's going to have two basis vectors. G1 will be 1, 1, and G2 will be 1, minus 1. So I want to compute, first of all, T of F1. So that's T of the vector 1, 1, 0. When X and Y are 1 and Z is 0, 1, 1, 0, I get 4, 5. And then I want to write 4, 5 as a linear combination of G1 and G2. Say A11 G1 plus A21 G2, which is A11 times this and A21 times this. I get A11 plus A21, A11 minus A21. So this equals 4, 5. So I'm solving the linear equations. A11 plus A21 equals 4. A11 minus A21 equals 5. If I add these equations, I get 2A11 equals 9. So A11 is 9 halves. And A21, this plus this is 4. This is minus a half. So if I take T of F1 and I write it with respect to this basis in R2, the coordinates are 9 halves minus a half, which is what I got a few minutes ago. That's a good sign. I want to compute T of F2, which is T applied to the vector 1, 0, 1. 1, 0, 1, 1, 0, 1, that gives me 6, 2. And I want to write 6, 2 as a linear combination of G1 and G2. So this equals 6 and this equals 2. If I add these two equations, the A22s cancel. I get A12 equals 8. So A12 is 4. 4 plus 2 is 6. 4 minus 2 is 2. So A22 is 2. So T of F1, T of F2 with respect to my basis has coordinates 4, 2. So that looks good. I want to compute T of F3. That's T applied to the vector 0, 1, 1. So when X is 0 and Y and Z are 1, I get 0, 1. And I want to write this as A13 G1 plus A23 G2, which is A13 plus A23, A13 minus A23. This is going to be 0, 1. If I add, I get 2 times A13 is 1. So A13 is a half, and A23 is minus a half. So T applied to the vector F3 and written with respect to this basis in B2 is a half minus a half. So I actually did it correctly the first time in terms of calculating the matrix. So what we get is that my matrix for T is, just writing down what I calculated already twice, 9 halves minus a half, 4, 2, 1/2 minus 1/2. So then, so I think I did everything correctly, and I only made a mistake, I guess, when I was doing my checking. So let's try to do that check problem again. So check. Suppose I let V be the vector -2, 0, 3 in R3. So what is the coordinate vector for V with respect to B3? This is going to be some x1, f1 plus, sorry, let me use some different letters here. So maybe, okay, sorry. Let me do it the way I did it, the example I started with. So suppose I take a vector V in R3, and the coordinate vector for V with respect to this basis is -2, 0, 3. So that means V is -2f1 plus 0f2 plus 3f3. What is that? 2f1 is 2 times, is minus, so -2 is -2 times 1, 1, 0 plus 3 times f3, which is 0, 1, 1. That's the vector -2, 3 minus 2 is 1, 3. So -2, 0, 3 is the vector -2, 1, 3 in R3. Let's apply the matrix T to this vector, this coordinate vector. So that's 9/2 minus 1/2, 4, 2, 1/2 minus 1/2, applied to the vector -2, 0, 3. So this gives me -9 plus 0 plus 3/2, -1 plus 0 minus 3/2. Sorry, plus 1, -2 times -1/2. So this is -9 or -18. That's -15/2 minus 1/2. So what this means is that if I take the vector T of V and I write it in coordinates in B2, it's -15/2 G1 minus 1/2 G2. That's -15/2. G1 was the vector 1, 1. G2 was the vector 1 minus 1. So I get -15/2 minus 1/2 is -8. -15/2 plus 1/2 is -7. So the coordinates for this vector in the basis B2 are -8, -7. So I start with the vector -2, 0, 3, and I get the vector -8, -7. Okay, so let's check now. So the vector V is equal to -2, 1, 3 in the standard notation. So T of V is what? So T is 5 times -2 minus 1 plus 3. And the second coordinate is 3 times -2 plus 2 times 1 minus 3. So this is -10 minus 1 is -11 plus 3 is -8. minus 6 plus 2 is minus 4 minus 3 is minus 7. It works, right? Perfect. So when we applied t to the vector v, and the coordinates with respect to b2 are minus 15 minus a half, but when you write it as in the usual way in R2, it's minus 8 minus 7. So t of the vector minus 2, 1, 3 gives us minus 8 minus 7. So everything is correct and the world is doing okay. That's good to know. Huh. All right. So everyone's quiet. So I don't know. I assume that means complete confusion reigns in the world. Maybe I'll look at the third problem here since I have a few more minutes. So this is exercise 3 on page 53. So in R2, let F be the basis consisting of the vectors F1, which is 8 minus 3, and F2, which is minus 5, 2. So if I take the vector v equal to AB, I want to write this as some linear combination of these two vectors, xF1 plus yF2. That's x times 8 minus 3 plus y times minus 5, 2. This is 8x minus 5y minus 3x plus 2y. So given any a and b, we want to solve the equations 8x minus 5y equals a minus 3x plus 2y equals b. So how we solve it is, two equations and two unknowns. We can eliminate the y by multiplying the first equation by 2 and multiplying the second equation by 5. And when you add, you get x is equal to 2a plus 5b. And we can eliminate the x by multiplying the first equation by 3 and multiplying the second equation by 8. And when we add, we get y is equal to 3a plus 8b. So the vector AB is always equal to 2a plus 5b times the vector F1 plus 3a plus 8b times the vector F2. So every vector in R2 is a unique linear combination of F1 and F2, and that proves that F is a basis. So in particular, let's see what we can say. If we take the vector, so this is 2a plus 5b times F1 plus 3A plus 8B times the vector F2. So in particular, if we take the vector E1, which is 1, 0, when A is 1 and B is 0, this is 2F1 plus 3 F2. If I take the vector E2, which is 0, 1, when A is 0 and B is 1, I get 5F1 plus 8F2. So suppose I have a vector V, which is xy. That is xe1 plus ye2. Let me do this on a bigger piece of paper so I have more room. Let me just write this down. So I have F1 is 8/3, F2 is minus 5/2, minus 5/2. This vector minus 5/2. And E1 is 2F1 plus 3F2. E2 is 5F1 plus 8F2. So if I have a vector V, xy, which means xe1 plus ye2, if I want to write it in terms of the f's, this is x times 2F1 plus 3F2 plus y times 5F1 plus 8F2. What is that? That's equal to 2x plus 5y F1 plus 3x plus 8y F2. Suppose I take the matrix with columns 2, 3, and 5, 8. So P of xy, 2, 5, 3, 8 times xy, that is 2x plus 5y, 3x plus 8y. Right? What is this? 2x plus 5y f1. So if this vector is v, the coordinates for v with respect to this new basis f are 2x plus 5y, 3x plus 8y. So this is the coordinate of v with respect to f. So what this equation says is this matrix P applied to the vector f with coordinates in E, the standard basis, gives me the coordinates of v with respect to f. So P is what is called the change of basis matrix. So if you have two different bases for a vector space, you can construct a matrix which changes very efficiently coordinates of a vector with respect to one basis to coordinates of a vector with respect to another basis. But this I will talk about in detail on Wednesday. Okay. Questions? Any questions I can answer about this? If you do have questions, and you are really encouraged, I have several more office hours this week. I think I have 2 today, in fact, one late in the afternoon and one in the evening. You're welcome to log on and ask questions, and I can explain things in more detail, I guess. Okay. Questions? Questions? If not, then we are done for the morning. Or it's afternoon now. We're done for the afternoon. Okay, take care all.
Thank you, Professor. Have a great day.
Thank you.